Okay, let's look at exercise 3, question 3. In this question, we are told that probability that a particular make of light bulb is faulty is 0.2. So this means that P is 0.2 and the light bulbs are packed in boxes of 12. Okay, so in this case, N is 12 if we are talking about in one box, number of light bulbs in one box. Okay, so first of all, the question asks you to state two assumptions needed for the number of faulty light bulbs to be well modeled by a binomial distribution. Okay, so we have learned that there are four conditions that must be satisfied in order for something, a situation, or an experiment to be well modeled by a binomial distribution. Okay, so from that four conditions, we will choose two appropriate ones to be used as assumptions that are needed in order to well model the number of faulty light bulbs by a binomial distribution. So the first condition is finite number of trials. So this is already stated in the question that there's finite number of trials, 12. So therefore, we do not need to assume this. Second condition is there are only two possible outcomes. So in this case, it is understood that either a light bulb, each light bulb is faulty or it is not faulty. So therefore, we also do not need to make this condition as an assumption. So therefore, the two assumptions which are needed will be the third and fourth condition. Okay, so the third condition is the probability of success, or P, must be constant for each trial. So in this case, okay, we can phrase it as this. Each light bulb is equally likely to be faulty. So this means the probability of success is constant for each trial. Okay, you need to fit it into the context of this question. So I need to remind you, do not just regurgitate, just memorize and regurgitate the conditions of the binomial distribution here. You need to fit it to the context of this question. Otherwise, you will not get your mark. Okay. So the fourth condition of binomial distribution is that the trials are independent. Okay. So in this case, what does it mean for the trial? The trial in this context is whether a light bulb is faulty. That is the trial. Okay, so the trials are independent. So in this case, whether a light bulb is faulty is independent of whether another light bulb is faulty. Okay, so you can see that the keywords for the condition is still there. Okay, so this will therefore be the two conditions which you need to make in order for a number of faulty light bulbs to be well modeled by binomial distribution. Okay, let's do some calculation now. Part A, find a probability that there are more than 3 faulty light bulbs in two boxes. So we know that in two boxes, there are a total of 24 light bulbs. Okay, because in each box, there's actually 12 light bulbs. So in two boxes, there's a total of 24 light bulbs. So we'll always need to start by defining our random variable. Okay, so let S be the number of faulty light bulbs in two boxes. So then after that, we write down the two parameters. X follows a binomial distribution with N. So in two boxes, there are a total of 24 light bulbs. And P is probability of each light bulb is being faulty is 0.2. Okay, so now after we have defined the random variable x and then write down its distribution, that means the value of the two parameters n and p, now we're ready to calculate. So probability x greater than 3. Okay, so in order to use binom CDF, we need to change it to less than or equals to. So probability x greater than 3 is equals to 1 minus probability x less than or equals to 3. And you just press your GC and you'll be able to get the answer. Okay, part 2. You're asked to find a probability that there are more than 340 light bulbs in each of the two boxes. In other words, we are talking about two boxes, but then each time we are only considering only one box, looking at one box at one time. So in each box, we want to find a probability that there are more than 340 light bulbs. And then after that, we want both boxes to satisfy this condition that in each of these two boxes, there must be more than 340 light bulbs. Okay, so now since the value of n has changed, is different compared to part 1. In part 1, we are considering in two boxes in total. So n in part 1 is 24. But then n in part 2, that means the number of trials at one time is just one box, so which is only 12 light bulbs. So once either the value of n or the value of p has changed, then you will need to define a new random variable. Okay, so we need to define a new random variable. We usually start with x followed by y, and then after that we will move to usually u or w. Here we do not use z because z is usually reserved for standard normal distribution, which you will learn about it in the next topic on normal distribution. Okay, so let y be the number of 40 light bulbs in a box of 12 light bulbs. So y follows a binomial distribution with n 12 and p 0.2. So we're going to find probability number of 40 light bulbs in the box is more than 3. Okay, but then what we want to find in part 2 is actually probability that there's more than 3 light bulbs in each of the two boxes. That means not only in one box, but actually in both boxes. It must satisfy this requirement. So it's probability y greater than 3 times probability y greater than 3. Okay, so it's 0.20543 times 0.20543. Okay, press your GC and run off to 3SF. Okay, you'll be able to get the answer. Okay, last part, which is part B. Okay, in part B, the question says a buyer accepts a consignment of boxes if when he chooses 3 boxes at random, he finds that they contain no more than 140 light bulb altogether. So 3 boxes altogether. Okay, no more than 140 light bulb. Then he will accept the consignment. So what's the probability that the buyer will accept the consignment? So he will accept if 3 boxes in total. That means total will be 36 light bulbs, right? So that will be our value of n in part B. So therefore, the value of n has again changed compared to the previous part. So we need to define a new random variable. Okay. Okay. So this is actually part B instead of part 3. So we need to define a new random variable. Let's use u. Since we already use x and y, let's use u now. Let u be the number of light bulbs out of 36 light bulbs. So u follows a binomial distribution with n 36. And p is still 0.2. So we're going to find probability that the buyer will accept the consignment. So for the buyer to accept the consignment, you're told that in total it must contain no more than 140 light bulbs. That means number of 40 light bulbs must be at most 1. Okay, no more than 1 means at most 1. So u is less or equals to 1. Okay, so this is already in the form where you can use binom CDF. So just press your GC. Okay, and you'll be able to get the answer 0.00325. Okay, good. So that's it for question 3. Let's quickly move on to question 4 now. In question 4, it is also a contextual question. So you're told that 80% are right-hander, 15% are left-hander, and 5% are ambidextrous. Okay, that means can use either hand, either left hand or right hand equally well. So again, to start the question asks you to state what are the two assumptions needed in order for the number of ambidextrous adults to be well modeled by binomial distribution. So the two assumptions will be um, again, probability of success must be constant for each trial. So to fit into this context, you will say each adult is equally likely to be ambidextrous. Okay, then the condition where the trials are independent. So you will say that to fit into context of this question, what does it mean for the trial? So the trial in this case is whether an adult is ambidextrous or not. Okay, so the trials are independent. In this case, it will mean whether an adult is ambidextrous is independent of whether another adult is ambidextrous. Okay, okay. So now we are done with assumptions. Let's do some calculation. In part A, if 10 adults from this country are selected at random, so this will be your value of n. Okay, find in part A for all the parts. Okay, so find the probability that at least one of those chosen will be ambidextrous. So now in part one we are concerned with ambidextrous adults. Okay, and then n is 10. So we'll start by defining the variable. Okay, so let x be okay. So in part one, we are concerned with number of ambidextrous adults. So we'll define a random variable as let x be number of ambidextrous adults out of 10 adults. Okay, because n is 10. So x follows a binomial distribution with n 10. And then what's the probability of an ambidextrous adult? We are told is 5%. So it is probability will be 0.05. 5 divided by 100 will give us 0.05. Okay, so we want to find part 1 at least one ambidextrous adult. Okay? So that is the same as 1 minus probability x less than 1. X less than 1 is only one value for binomial distribution, which is s equals to 0. Okay, so now for s if it's equal, we can use binom PDF. Okay, and just key into your GC to work out probability x equals to 0, and that answer, that value, we just use 1 minus that value, and you will be able to get the answer for part 1. Okay, let's look at part 2. Part 2, we are concerned with, we want to find what's the probability that more than 6 out of these 10 adults will be left-hander. So now we are concerned with left-hander, number of left-hander adults, okay, out of these 10 adults. So since the random variable that we are concerned with now has changed compared to part 1. Okay, so we need to define a new random variable. In part 1, the random variable that we are concerned with is about number of ambidextrous adults. But in part 2, the random variable that we are concerned with would be the number of left-handed adults. Although the value of n in part 1 and part 2 remains the same as 10, but then the random variable has changed. Okay, so in part 2 compared to part 1. Now we are looking at number of left-handed adults in part 2. So therefore, we'll need to define a new random variable in part 2. Okay, and the value of P has also changed. So now probability of a left-handed adult will be 15% or probability of 0.15. So we want that there is more than 6 left-handed adults. Okay. So change it to the form where you can press your GC for binom CDF. Okay, and you get your answer. Okay, let's look at part 3 now. Part 3, we want to find at most 4 will be right-handed. So now the random variable we are concerned with in part 3 is again different from part 2 and part 1. So therefore, we need to define a new random variable because now in part 3, we are concerned with number of right-handed adults, which means that the value of P will be different in part 3 compared to the previous parts. So we need to define a new random variable, okay, for right-handed adults. Okay, so we use random the variable, the alphabet T. Let T be number of right-handed adults out of 10 adults. So T follows a binomial distribution with N is 10 and P, probability of right-handed adult and adult being right-handed will be 80% or probability of 0.8. So what do we want? We want at most 4. At most 4, so that means probability T less than or equals to 4. So we can straight away press GC now, 0.00637, okay, because this is already the inequality sign for that we can apply binom CDF. Okay, part 4. Part 4, so we are concerned with right-handed adults and then less than 3. So the random variable and the value of P in part 4 is the same as part 3, so which is number of right-handed adults. So the value of P remains the same as 0.8. So therefore, we do not need to define a new random variable in part 4. We can just use back the same random variable as in part 3. So we want to find less than 3 will be right-handed. So that means T is less than 3. Okay, so it means T is less than or equals to T is less than or equals to 2. Alright, so we can press GC. Which gives us a probability of 0.000097779, which is a very small, extremely small probability for the number of right-handed adults out of 10 to be less than 3. Okay, because actually based on the probability of success, right-handed adults actually make up the greatest probability. Okay, in fact it's 0.8 for the probability of success. Okay, now let's look at part 5. In part 5, you are given that there are more than you're told that there are more than one ambidextrous adults given that, okay, in a sample of 10. So n is still 10. For a probability that there are at most 4 of those chosen who will be ambidextrous. Okay, so at most 4 of those chosen will be ambidextrous. So part 5 is actually a conditional probability question. Okay, it's a conditional probability question. So this is the first thing that you will need to be aware of. Okay, so number of ambidextrous adults, you can use the same random variable as part 1. Okay, part A, part 1, which is X. Okay, so there's no need to and also because value of p remains the same as 0.05 and value of n, number of trials, remains as 10. So we can use back the same variable, which is x. Okay, so we want to find probability there are at most 4 will be ambidextrous, given that there are more than one ambidextrous adult. So given that x is more than 1. Okay, so probability x less than or equals to 4, given that x is more than 1. So we rewrite it in the form of the formula for conditional probability, and then we look at the numerator. What does it mean for x less than or equals to 4? And x intersect with x strictly greater than 1. So it means x must be greater than 1 but less than or equals to 4. Okay. And then denominator, probability x greater than 1. Okay, we keep it as such first. So now what does it mean? It means x is greater or equals to 2, less than or equals to 4. Denominator, again, we just keep it as such. Okay, now numerator, we can rewrite it as probability x less than or equals to 4 minus probability x less than or equals to 1. Denominator will be 1 minus probability x less than or equals to 1. Okay, so once we've changed numerator and denominator to be the form where we can use GC, then we can now press GC. Okay, because for all this, we can use binomial CDF to calculate. Okay, good. So that will be for part 5. Now, let's look at part B. In part B, you are asked to find least value of n such that probability of obtaining at least 3 left-handed adults in a random sample of n adults exceeds 0.06. So now, in part B, what are we concerned with? Left-handed adults. Okay, so we have already defined the random variable for left-handed adults in part A, part 2. But can we use back the same random variable as part 2? No, we cannot. Because in part 2, in part A, part 2, the value of n is 10. But in this case, in part B, the value of n is unknown. Okay, so the number of trials which is represented by n is unknown. In fact, that's what we are asked to find in part B, least value of n. So therefore, we cannot assume or we cannot take it that the value of n in part B is the same as in part A, part 2, which is 10. So therefore, in part B, we need to define a new random variable. Okay, in part B. So let's use a random variable which we have not used so far in this question. We can use u. Okay, so let u, random variable u, be number of left-handed adults of n adults. So u follows a binomial distribution with parameter n, and probability of success of left-handed adults will be 0.15. So what do we want? We want probability of obtaining at least 3 left-handed adults to be greater than 0.06. So probability u greater or equals to 3 to be greater than 0.06. Okay, we need to do some conversion to the form where we can use binomial CDF. Okay, so finally we change it to probability u less than or equals to 2 is less than 0.94. So this is the probability that we are going to use. So we can use GC to help us to get the values, okay, for least n that satisfy such the left hand side of this inequality will be able to satisfy will be first less than 0.94. So we key in into our GC. So this part we key in left hand side into Y1 of our GC. Okay, and then we use GC table. Okay, so in our presentation, so GC table to see when is it that the value of n will cause probability of u less than or equals to 2 to first be lesser than 0.94. Okay, so we copy down from our GC the values. Okay, so please try out on your own that you are really able to obtain all these probability values, okay, from your GC. Okay, so from a GC, this is what we notice. So when is it that probability, the left-hand side probability of u less than or equals to 2 is first less than 0.94. So this is still greater than, this less than, this less than. So when n is 7, n equals to 7, probably the left side probability will be the first time that the probability value drops below 0.94. So therefore, least n is 7. Okay? Okay, this is a super long question. Finally, we are down to the last part, which is part C, okay, of this question. In part C, you're asked to find greatest value of n if in a random sample of m adults, probability of at least one right-hander is at most 0.96. Okay, so now in part C, what are we concerned with? We are concerned with right-handed adults. Okay, right-handed adults, and the sample size is m, which we do not know what is the value of m. So in fact, we are asked to find what is the greatest value of n. So we cannot assume that n in this case, or the number of trials is actually 10, which is in part A. So we cannot assume that. So therefore, although it's talking about right-handed adults, but the number of trials is unknown. So therefore, in part C, we need to define yet another new random variable for part C. Okay, so let's use another alphabet. We have not used W, let's use W. So let W be number of right-handed adults of M adults. Okay, so the question say we want probability W greater or equals to 1 to be at most 0.96. Okay, so probability of at least one right-handed adult, that means probability W greater or equals to 1 is at most 0.96, means less than or equals to 0.96. Okay, so change it to the form where we can use GC. So 1 minus probability W less than 1 means W equals to 0. Do some rearrangement and we'll arrive at this inequality, okay, which is probability W equals to 0 is greater or equals to 0.04. Okay, so now again we will use GC. So the left hand side we'll treat it as Y1, okay, and then we key into our GC and then we use GC table of values. Okay, to display, and this will be the correct answer will be m equals to 2. So we'll copy one row above and one row below. Okay, so we'll see that where m is 1, probably the left hand side probability w equals to 0 is 0.2, which is greater than 0.04. Where m is 2, the left hand side probability value is 0.04. So 0.04 is still greater than or equals to 0.04. Okay, because then 0.04 is actually exactly equals to 0.04. So therefore, where m equals to 2, the left hand side probability value still satisfy the inequality. Okay, but when m equals to 3, the left hand side probability value is 0.008, which is less than 0.04. So therefore, m equals to 1 and m equals to 2 both satisfy this inequality. But the question asks for greatest the question actually asks for greatest value of m. Okay, so greatest m between m is 1 and m is 2, greatest m will be m is 2. Okay, so that will be the answer for part C of this very long question. All right.